Hello everyone. Well, today we'll go through the line integral and how to use the scalar and the vector definition of these integrals to evaluate some kind of specific application using these line integrals. So first, if we have a scalar integral, it means we have a line integral. So we are doing this integration from some points in space P and some other point in space Q, and there is some kind of path here, which is C, and we need to evaluate this function, which is f, along this path, which is open path right now from P to Q. So this can be in 2D, and also it could be in 3D. So it means it could be just in X and Y, and more generally, could be in the 3D space, X, Y, and Z. In both cases, we have this function f is function of x and y, or more generally, f could be x, y, z. And then ds represent a small part of this path here, and this is our ds. If we are speaking about x, y, z generally, so ds will be the dx squared plus dy squared plus dz squared. So the length of any vector in the space is just the square root of squares of each one of these components, x, y, z. If we are just speaking in 2D, so ds will be nothing but dx squared plus dy squared. In case of parameterization, it means I have x as some function of t, and also y as a function of t, and maybe we have z as a function of t as well. So ds can be written as dx by dt squared, dy by dt squared, dz by dt squared. And then all of these terms multiplied by dt. Again, in case of parameterization for a special case in 2D, so ds can be written as dx by dt squared, dy by dt squared, and then everything multiplied by dt. So this is one form. So this, again, it will be a line integral. It means it's integral over one variable at the end. So this is what we called here the scalar. Scalar, again, line integral. So let's see. Here it's required to find the value of the integral x squared plus y squared plus z ds along the curve C, and C is given as the part of the helix parameterized by r of t, where this r is defined by this one, like this represents this x of t, and this represents this y of t, and this is represent your z of t. And then this t is from 0 to 2 pi. So first of all, if we need to calculate this integral, so this I will be equal. We have a value for each one of them along the path. It means I can substitute here. So the first step, I will be substituting with x, y, and z as function or functions of t, and then get ds also as a function of dt, and the third step will be just the integral with respect to t. So here this integral will be x squared, which is cosine squared t, plus y squared, which is sine squared t, plus z, which is t, and again this is nothing but substitution of this part to be this one. And here we'll end up with ds. So ds, we can put it here again, the same form. So it's dx by dt all squared, dy by dt all squared, dz by dt all squared, dt. So if we are trying to calculate this value, so this one will be dx by dt, x is cosine, so this will be minus sine, squared, dy by dt, y is the sine, so this one will be cosine t, and the squared, and dz by dt, which is 1 squared. So this one will be nothing but root 1 plus 1 plus root 1 like sine squared plus cosine squared is 1, plus the other one would be 2, so root 2d. So right now I can write down this integral as cosine squared plus sine squared, these together is just 1. So this will be 1 plus t. And ds, it's nothing but root 2 dt, and the integral from 0 to 2 pi. Again, this root 2 is a constant. T1 will be integrated as t. T will be t squared over 2. And substituting with this 0 and 2 pi, 0 for sure will be 0. And then this one will be root 2, 2 pi, plus the other term, which is 4 pi squared over 2, which is 2 pi squared. Getting this 2 pi common, so it will be 2 root 2 pi, then we'll end up 1 plus pi. And then this is the value of this integral. What this value means? It means it's the integration of this function here, which is x squared plus y squared plus z, over the path defined with this like location, which is cosine t, sine t, and t. So what happened if we doing the same, but instead of having a function, we need to find the length of this arc. So the length of this arc, let's remember, we got just r of t. It was here cosine, sine, and t. So this one here, we can consider it as, and also see t's value as between 0 and 2 pi. To find the length, it's nothing but the integration of this ds, and there is nothing to be integrated except just 1. And ds, we got it from the previous example here. It was root 2 dt, and t we have this value from 0 to 2 pi, so it will be root 2 and then multiplied by 2 pi. So what this value means here? This means this arc, which is part of this helix for anything. So it would be any helix here. And the length of this part is root 2 multiplied by 2 pi. So if we have a function as any kind of like multiple variable integrals, we have a function, we can integrate this function to find the total value of this function over this length, or there is no function, so this one will be 1, this one will be just your length. As in the area, integration of 1dA is the area, integration 1dV is the volume. If there is a function f, so this means this will give some physical meaning. So this could be density give you the mass, or some like charges per unit length, it will give you the total charge. So it depends on what the value of this f represent here. If it's the force, so this will give you the work. Like anything changing per unit length, the integration over the whole length will give you the whole value of this function over the total length. So let's move forward. As I stated in the previous description of this is scalar integration. Here it's required to find the mass of the spring wire in the shape of a curve parameterized by t, 2 cosine t, 2 sine t, where t from 0 to pi over 2, with a density function given by this 1 kilogram per meter. So this function here, it's rho, and I need to figure out the mass. So for sure this mass, it will be the integral of this rho, and the integration with respect to the length s or L. Doesn't matter the name of this variable right now. And we have this location or the curve parameterized with some formulas, which has this t as this is your x, and 2 cosine t, this represents y, and 2 sine t, and it represents z. So again, the s will be the same formula, dx over dt squared plus dy over dt squared plus dz over dt squared, and the sum of the squares under the square root, and then dt. To substitute with these values, so this will be 1, this will be plus minus 2 sine squared t, or what's it in the right way? It will be minus 2 sine t squared, and the other term will be 2 cosine t squared, and again the square root dt. So this one will be root. We will have here 4 sine squared, 4 cosine squared. So taking 4 common, it will be 4 sine squared plus cosine squared, which is 1. And we have 1 outside, so this will be root 5 dt. So this is our ds. Returning back to this one here. So rho here is e power x, which is e power t, plus yz, which is 4 cosine t sine t. We have this ds at the end. So just one step for simplification. This one will be e power t, and this 4 cosine sine, it's nothing but 2 sine 2t, and then this ds here, it's root 5 dt. and t is given from 0 to pi over 2, which we can find here. So this mass will be integration from 0 to pi over 2 root 5 e bar t plus 2 root 5 sine 2t. Let's integrate this together. So this root 5 e bar t will be the same exponential. And the other thing, this sign, it will be minus root 5 cosine 2t, and from 0 to pi over 2. Let's substitute here. So this one will be root 5 e powered pi over 2 minus e power 0, which is 1, minus root 5 cosine pi, which is minus 1, minus cosine 0, which is 1. So here we can give the mass as a value, root 5 common, and we will end up with e pi over 2. And we have here minus 1, and we have from this term is plus 2. So this one will be plus 1. And this is the mass of this wire spring. So again, we have this density, which is linear density, means the mass per unit length. And we have this curve parameterized as a function of t. We got this ds from this simple formula, dx by dt squared, dy by dt squared, dz by dt squared. And then after simplifying this ds as a function of dt, return back here and substitute with ds and also with rho as it defined along this spring wire with these corresponding values of x, y, z. We did all these substitution and then the last simplification step. We end up with this m here, and this m for sure is kilogram unit. So let's move forward to the other one. And instead of having f defined as a scalar function, like what we did previously as defining the length or the mass or a charge, we need right now to find the integral of some vector quantities. So this is the other type of in the linear or in the line integral. So the vector integral, we have this line integral of f defined as a vector dot dr or dot ds, doesn't matter again. We have this c, which is our path here defined. So we have c defined by some function x, y, z, or even by some parameters t. So how we can do this integration? We'll do something in the vector form instead of the scalar we did previously. So again, we can express dr as r prime dt. What's this r prime? Just the vector form of the scalar ds we did previously. So it will be dx by dt in the I direction, dy by dt in the j direction, dz by dt in the k direction. And then we can do this dot product, and afterwards we can integrate with respect to t. So this will be very helpful if we need to do some kind of integration related to some forces to find the work. So this could be defining the work for some kind of special vectors representing the force, or any other kind of vector formulas for this fields. So here, let's Let's see how to solve this one. It's required to find the work to move an object in a vector, and this vector field is f given by this one, y, z, x, y, x, z, along the path r of t given by these parameters t squared, t, t power 4, and t is defined between 0 and 1. So what we can consider here at this moment, if we need to find the work, so this work will be the integration of this vector field f dot dr. What's this dr? Again, so this one will be yz, this in I direction, the other part is xy, this j direction, xz in k direction, dot product with r prime. R prime will be, instead of t squared here, this one will be 2t, I direction. In the second term, it will be 1 in j direction. The last term will be 4t cubed in k direction, and all this integral with respect to t. Again, don't forget this y and z already given, so we have x will be substituted by t squared, y equal t, z equal t power 4. Substitute with these three quantities here, we'll end up with this work equal yz, it will be t power 5, and xy, which is t cubed, and xz, which is t power 6, and then dot product was 2ti plus j plus 4t cubed k dt, and t is defined between 0 and 1. Doing this dot product, so the first multiplied by the first, so this will give us 2t power 6. The second term will be t cubed. The last term will be 4t power 9, and the integration with respect to t. It will be 2t power 7 over 7, t power 4 over 4, 4t power 10 over 10, substitute with 0 and 1, and then doing the simplifications, this will give us at the end 131 over 1. And then this is what we can call this is the simplification of this value here. So what this value represent? This value here represents the work done by this force, which is given by this yz in the x direction, xy in the y direction, xz in the z direction, along this path here, which is given by this r, which is this vector defined by the parameter t, defined by t squared in the x direction, and t along y direction, and t power 4 along z direction. This t defined between two values, 0 and 1. So these are limits of integration. And then after substituting here, we can get the value of this line integral. So let's see also something here. There is some definition regarding this vector integrals, and this came from some physical meaning of this vector. If we have a conservative field or conservative force as a vector, and this vector is defined by any function p of x, y in x direction, and some other function x, y, and j direction, we are assuming 2D vector. This could be generalized also in 3D by adding a third term in the k direction. We need to check something first. If the derivative of the part of this vector along I with respect to y, so this is here, will be derived to y, and the other term which is in the y direction, which has the j, will be derived with respect to x. If both derivatives are equal, so here this will give us some special meaning for this vector. So we call this vector right now, it's a conservative vector field, or we can call this, if it's a force, we call it a conservative force. And this condition here is called the cross partials. So cross partials, it means the function in the x direction will be derived with respect to y, so this partial derivative with respect to y, and the other part of the vector which is in the y direction will be partially derived with respect to x. And if these both cross partials are equal, then this field or this vector, whatever it represents, it's called a conservative field, conservative conservative force. Again, it depends on what physical value this vector represents. Why this is very important? It's very important due to this both properties here. If we are doing integration over any open path from one point to the other, as we did in the previous few examples, this integration will be independent of the path. So this means, assuming we have some path from some point here 1 to point 2. Previously, if you are integrating along this path, if you are integrating along this path here, the value of this integration, it will be completely different than this path. It will be also different from this path. It means generally the line integral or any other integral, it depends on what path will go through the first point to the end point. But if our vector of inside the integration here is conservative, so this means all the paths will give you the same value for the whole integral between the first and the last point. Which means if I have a very complicated path to go through this integration and the force is conservative, you just get or just do this integration over the best one of them. What's the best one and which one is the easier to perform this integration? The best one for sure, it will be moving along the axes, x-axis and y-axis, and if we have this in 3D space, it will be along x, y, z axis. So each time you are just moving along one axis, which very simple. We can check this shortly. The other part, which also very helpful if we are doing some closed path integration. So it means our path here, we're starting from one point and rotating some direction and returning back to the same point. If our path of integral here is closed, so the integral over this closed path equal to 0. And this is one of the physical definition of the conservative force. If we have any kind of vector which is defined as a conservative, it means the work done by this force over a closed path, it will be 0. So this is also one of the physical definition from this conservative field or conservative force. So let's see in some examples here. Here we have this one right now, this example number 4. We have a vector field. So this is a vector formula right now. It's x y squared plus 3x squared y in I direction plus x plus y multiplied by x squared in the j direction. And it's required to find the line integral of f along C. What's this C? It's the curve consisting of the line segments. So we have some curve and we have some line segments. So let's consider this one here. This is x and this is y. And we have 1 and 1. And then we have 0 and 2. So this is 2, for example, here. And we have, like, this is 2, this is 3, and we have 3 and 0. This. So here again, we need to move forward from the line segments 1 and 1, 0, 2 was the first, and then moving back to this one. So this is our starting point. This is a start, and this is the end. Some sample question at the beginning. Do we need to go through this whole path, or our f here, this vector field, is conservative, so we can choose whatever it's easier for us. So these to be done need to be checked. So I will check if we have f, this f is equal some function in I plus another function in j. So what I will be doing, I will get the derivative of this p with respect to y and the derivative of this q with respect to x. The derivative of b with respect to y, it will be 2yx plus 3x squared. The derivative of q with respect to x, don't forget this x squared outside the bracket, so this x cubed, it will be 3x squared, and then this x squared with y, so this will be 2xy. As we can see right now, both of them are equal, so it means this f is conservative. It means the integral of f dot dr along the C is independent of the path. So I need to choose whatever path seems to be easiest one. So I need to move from the start point to the end point. So okay, I need to choose whatever is easier. So the easiest, as I mentioned previously, just moving through this line parallel to the axis. So I will choose this one and then this one. This is my C1 and this is my C2. If we are defining these lines, so this line integral, I can define it as integral over C1 plus another integral along the line C2. C1 and C2, we can write down here. C1 is something parallel to y-axis. I'm moving from y equal to 1 to y equal to 0. And we have something very special. X is constant over the whole path, so x equal to 1. So it means there is no change along this path, so dx equal to 0. Regarding C2, is the x-axis. So my x is changing from 1 to 3. And also here, y very special, it's equal to 0. So it means there is no change along this path. Putting this into consideration, I can get here this I, and for sure, whatever this path will be, the first one will be integral with respect to c1, so it will have dx equal to 0. So the other term will be integrated, x plus y, x squared, and this will be integrated with respect to y, and the other term, which is c2, it will be dx as dy equal to 0, so this will end up xy squared plus 3x squared y, and this one dx. So see, so considering this one right now, sorry, I need to move through C1. We mentioned that C1, it will give us some change along y-axis. This is x and this is y. So this C1, I will have this y, it changing from this value here right now, which is 1 going down to 0, and x is constant equal to 1, and dx correspondingly is 0, so there is no change in x. C2, I have just changing in x, so x happens to be the values between 1 and 3, given that y with no change at all, so y is equal to 0, it's just lies on y-axis, and dy correspondingly is 0. But here I mentioned this is our C. What was the previous one? So going this way and return back to this way. So instead of doing this whole hassle, we have this conservative field. So the integral will be independent of the path, and we selected the easiest one of these paths. But what about this ds? ds, it's something very easy. We don't need any parameterization or something. Regarding the first path, which is C1, ds is nothing but the vector along the C1. So ds here is just equal to dy, and this is in j direction. And regarding C2, this ds, which is any change in the length of this line, C2, it's just an element dx, and it's in y direction. So here, we can easily, as we did in the previous slide, we got this along C1 and the other integral along C2. The first one was this f, which is pi plus qj, and then C1 is nothing but dyj. And I repeat it again, here this f, and then along C2 it's nothing but dxi. So it means when do this dot product, this term will be cancelled, the other one here it will be cancelled, and we will end up with I equal Q, which is this term. This is Q. This is what I'm calling here P. So this Q dot dy, it will be Q dy, and taking into consideration that along this one here, your x equal to 1. This is very special to this line. And here, taking into consideration that your y equal to 0. So let's do this together. So I have this first integral q dy, which is here x plus y x squared dy, and the integral along y from 1 to 0, and substitute with x equal to 1. So this one here, term will be 1, and this term will be 1. This is the first term. The second term will be plus the integral of p dx. P is x y squared plus 3 x squared y, and then integration with respect to x. X here is moving from 1 to 3, but don't forget that this y equal to 0, so this term 0, this term 0. So this whole term be 0. End up with the first one, so this I will be integration from 1 to 0, and we have 1 plus y dy. Here it will be y plus y squared over 2, substituting with the same order of these limits. So 0 will give you 0, and then this one will be minus 1 plus half. So this again, it's minus 3 over 2. What this value at the end? This is the value of the integral along the best path we can select due to this conservative force in our integral. Again, just moving through this one very quickly. We have this our f, and this is dot ds. We simplified this in the previous slide, but let's do it here in more details. We mentioned that C1 here is just dyj, C2 is dx along I, and we did this dot product. We'll cancel each like different components. So here in the first term, just y component or components with j unit vector will remain. The other parts will be cancelled out. And the second integration, the other parts rather than I components will cancel out. So q here will be cancelled. And also consider that at each C1 and C2 there is some specific values for x and y. So C1 has x equal to 1 and dx equal to 0. C2 we have y equal to 0 constant and dy equal to 0. So after substituting with all these values together, we end up with a very easy integral, very simple formula. 1 plus y will be y plus y squared over 2, integration from 1 to 0, end up with minus 3 over 2. So let's see something else. We talked about this closed path integrals. So here this is one of the very important, or maybe the most important thing in the line integral, which is the green theorem. So green theorem here, it relates what happened in the closed path as a line integral and what happened for this value of the integral if it could be possibly calculated using the area enclosed by this line or the closed path. So first, if we have a line integral of any vector here, this vector is f, and I need to get this f to be integrated over a closed path C. Green's mentioned that the value here of this integral is equal to the integration over the closed area here, or sorry, the area enclosed by this closed path, which is called here this region D, of this derivative in order, which is q derivative with respect to x, the partial derivative, minus p partially derived to y. Again, don't forget this f was nothing but this p, and I component, and the other part is Q, the J component. And P and Q, both of them are function in X and Y. So if we have any vector F, and this vector F has this P and Q, instead of doing this line integral, and maybe you will end up with something like this. Let's see. You can go through this line and then another line and another third line, fourth line, moving with multiple directions here and multiple segments. Instead of doing this 1, 2, 3, 4, 5, 6, 7, 8 integrals easily, just compute the integral over this region surrounded by this closed path. And this is what green theory implies. So what we are doing right now, if we have F, so we need to get this partial Q by partial X and partial P by partial Y. And then we can subtract each other and substitute with this formula. And then we'll end up with a simple integral over the region D, which is a double integral in this case. So what green theorem at the end, just to summarize all the aspect of this theory, we are transferring the integral from one integral with respect to this closed line integral to be a double integral for the region surrounded by this closed line. Let's see a quick example on this to illustrate the benefits of this theorem. Here it's required to calculate the work on a particle by a force F, and this F is given with this vector right now. As the particle traverses circle x squared plus y squared equal to 4 exactly once in the counterclockwise direction. So here we have the circle, which is x squared plus y squared equal to 4, and the particle is moving along this one counterclockwise. Something I forgot to mention in the previous slide, the integration of both terms, the double and the line, are equal in the sign and the value, considering that the line integral of this closed path with the direction counterclockwise, so it's anti-clockwise direction. It means if we are getting this integration with the clockwise direction, it will have a minus sign as we are flipping the limits of the integral. So the difference between both of them will give us the same value exactly, but with different signs. Counterclockwise would be the correct sign. If we are considering the clockwise direction, it means we flip the end and the start point. It means we will end up with a minus sign with the same value. So here we have this counterclockwise, so that's fine. And then we need to get this work. So work for this closed vector, it's this f dot ds over this closed curve. According to grain theory, this can be done as integration over the region, and again this qx minus py integration over the area. Where is q here? Q is y plus sine x. Sorry, it's not q. This is p, and q equal e power y minus x. It means py equal to 1, qx equal to minus 1. So the integral can be written as minus 1 minus 1 d area over this whole area here. So this is our curve C, and this is right now, this is the region D. So I need to calculate this over this region. For sure, this region is a circle, so it means in double integral, easier to use polar coordinates. So this one will be minus 2 r d theta, and r from 0 to 2. This is the radius and the angle between 0 and 2 pi. So here this will be minus 2, and this r squared over 2 from 0 to 2, and theta from 0 to 2 pi. So this will end up with minus 2 divided by 2 pi, and then this r2 squared, it will be 4 over 2, it will be another 2, so this will be minus 8 pi. So what does this value represent here? It represents here the work done on this particle moving with this force. So it will be, after one cycle, it will have a work of minus 8 pi. Some basic question, what happens if Py equal Qx? Means this work will be 0. Why? From the definition of this green theorem, we'll have both terms equal to each other, so again the work will be 0. But this is not the case in this example. So let's see another example here. It's required to calculate this integral, which is sine x squared dx plus 3x minus y dy. And C is a right triangle with vertices minus 1, 2, 4, 2, 4, and 5. So this means we have here this x and y. We have a point minus 1, 2, and then we have another point 4. So this 1, 2, 3, 4, and 2, and another point 4 and 5. Assuming this 4, so this will be 5, for example, here. And then this is our triangle, which is the right triangle as mentioned. Again, we have the C, and assuming the C here, the counterclockwise, so this is our C. Using green theorem here, this integration over the closed path of this f dot ds, b integration over the region D. This is our region here. Again, q x minus py d area. We need to get p, q, and then their derivatives. P is sine x squared, q is 3x minus y, means this py equal to 0, this qx equal to 3. Substituting in the integral, we'll end up with this qx equals 3, and then the area over this region D. Regarding this integral, so doesn't matter what kind of stripe we'll start with. So let's start with this horizontal strip here. So I can assume this 3. I'll start dx and then dy. Dx here from this line to this line. This line here is, like this one is x equal to 4. So here, this x equal to 4, this is the end one. The line here, it's between -1 and 2, and here between 4 and 5. So to get this line equation, we have this formula, like we have the difference, like y minus 2 divided by x plus 1 equal the difference in y's. So this is 5 minus 2 and 4 plus 1. So this 3, this 5, so this is 3 and this is 5. Means we have equation here right now. So 5y minus 10 equals 3x plus 3. Means I need equation for x, so 3x will be equal 5y minus 13. Means x at the end 5 over 3y minus 13 over 3. So this is the relation of this x line. So this will be here 5 over 3y minus 13 over 3. And y will be moving from the bottom to the top between y equal to 2 till y equal to 5. So again, this I will be equal 3. This is constant. The x will be integrated to bx. And then integration from 2 to 5 of 4 minus 5 over 3y minus 13 over 3. And all these terms integration with respect to y. So again, one will be 3, and we'll end up this 4y minus 5 over 3y squared over 2 plus 13 over 3y, and this limits from 2 to 5. So I will be this value,